back. It's time to continue on with our discussion of scatter plots. And this time we're going to focus in 4.2 on what we call measuring strength. Remember how we talked in 4.1 when we were talking about the strength, we were looking at the scatter plot, and it was all about, how the closer your points were to what we would call, to where it would look like a line. So like all of your dots, the closer they were, the tighter together they were to form a straight line, the stronger the relationship between the two variables there was. Okay. And the further away those dots were vertically from each other, the weaker the association. Okay. So in here, because in 4.1, that's very subjective. In 4.2, we're actually going to put a number to it. Okay. And this number is going to tell us how strong and how weak we are. All right. And so this number, it has a name. It's what we call the correlation coefficient. And just as I said a moment ago, it is a number that measures the strength of a linear association between two numerical variables. It only works if they're both numerical. And it only works if it looks like a line. It's linear, linear, linear. We do not talk about a correlation coefficient on nonlinear, okay? And again, I will stress that a little bit later on, just like our book stresses it. If you read our book, which is really, really good, our book is a good read, just so you know. All right. So again, just what I said right there. It only makes sense if the trend is linear and both variables are numerical. All right. So how do we find this correlation coefficient? It looks like this. R represents the correlation coefficient. And what you're going to do is you're going to add all of the products of the z-scores of every x and the z-score of every y. And then you'll take that answer and you will divide it by n minus 1. Okay? That formula is nuts. Okay? Because remember, a z-score is where you're going to take the value minus the mean and divide it by the standard deviation. So for every point you have, you're going to find the z-score of the x value, the z-score of the y value, and multiply that, and then add all those answers up. Again, doing this by hand is crazy. There is no reason you should be doing a correlation coefficient by hand. I'm going to show you how the calculator can help you out with this, and I'm going to show you how StatCrunch will figure this out. But this, I wanted you to let you know, there is a formula for it. This is how it works. You take every point, find the z-score of x, the z-score of y, and you're going to multiply those together for every point. Add all that up, and then divide that answer by n minus 1. And R is what we call the correlation coefficient. Okay? So that you know, the correlation coefficient is a number that falls between -1 and 1. And it can be equal to -1 and it can be equal to 1. Okay? So this answer cannot be any bigger than 1 or any smaller than -1. It lies between -1 and 1. Okay? So just some extra information about the correlation coefficient. When R is close to -1 or close to 1, then it means that you have a very strong association. Okay? The closer you are to -1 or the closer you are to a +1, the stronger the association. The closer R is to 0, the weaker the association. Couple other things, just so you know. A positive R value yields a positive trend. It should look like the idea is it should look like a positive slope. Please know that R is not slope, but the value, the sign of R tells you what kind of slope you should have. If the R value is positive, then that means you should be looking at a positive slope, which more about slope when we talk in 4.3. If your R value is negative, then it should look like a negative trend. It should have like a negative slope to it. Okay? And then last but not least, well, actually not last but not least, just a couple other things. Changing the order in which you compare the two variables does not affect R. Okay? Changing the order of the two variables does not affect R. I'll show you what I mean by that here in just a second. Adding a constant or multiplying by a constant to each point does not affect R. Again, I'm going to show you what that means here in a second. So I can add a number to every x value, and it's got to be the same number. So if every x value gets added the number 2, the R value will still be the same as if we didn't add the number 2. If I take every y value and multiply it by 5, that's going to give you the same R value as if we didn't multiply by 5. That's what this is meaning. And I'll show you this when it works, as it works here in a second. That's what I'm trying to say. Know that R is unitless. It is unitless. It doesn't contain any units. It's basically just a number that tells you the strength. Also, please understand, I think I stated this in 4.1, but I'm going to state it again. Just because there's a correlation, just because it might be really strong or really negative, okay, a strong negative, does not mean it causes, those two things cause each other, okay? So just because we have a correlation, it does not mean causation, okay? And again, I'm going to give you an example of that here in just a moment, all right? So let's talk about some things. So here, these are graphs. And what you see right here in each one of these graphs, the scatter plots, you can see the correlation coefficient. There's when R is 1. Here's when R is 0.9. Here's when R is 0.72, 0.48, 0.19, and 0. So you can see that as that value of R gets closer to 1, it looks like a line. As that R value gets closer to 0, the line goes away. There's no trend. Okay? So you can see that there's much more scatter here. Okay? So this kind of illustrates what we were talking about before, where the stronger you are, the closer your dots are together and forming a line. So here, when the relationship is 1, see, look at that. It's a perfect line. But over here, as we start to deviate, as there's a little bit more variation vertically, as my dots separate vertically, my R value starts to get a little bit lower. Okay? So the bigger that vertical separation, the lower the R value. That's what we were talking about in 4.1, this vertical separation. See how there's lots of vertical scatter there? That's made my association just a little bit weaker. I mean, we can see the trend. We can see it's positive. And notice that my R value is positive. But there's just a lot of vertical distance between our dots, which is why our R value is lower. So the more and more your dots start to separate from a line, and there's lots of vertical separation, the closer to 0 your R value gets. Right down here, just what I was saying. In the other direction, here is R when it's 0. Here is a negative 0.36. Negative 0.56. Notice it's starting to form that line right there. Dots are moving a little bit closer. Negative 0.79, getting closer and closer. There's a negative 0.9. So you can see kind of like a thick line there. And then a perfect negative 1. Okay? So Couple things that I was talking about a moment ago. So one of the things was that if you change the two variables, it will not affect the R. So this R value of 1 right here that you see, if I put this height in inches over here and this height in centimeters over here, the R value is still 1. Now the slopes will not be the same. The equation of the line will be different, but the relationship between these associations is still 1. It's still strong. That's what I mean by it doesn't matter, changing your X and put it in for Y and your Y and put it in for X. The R value is still the same value. And the same thing over here. Men's life expectancy versus women's life expectancy. If I flipped these two, yes, the picture will change a little bit, but these dots are still going to be clumped together like this. Okay? Yes, the slope of my line will be a little bit different. The equation for this line will be a little bit different, but the R value is still going to be 0.98 if I have the women life expectancy down here and the men's life expectancy right here. Okay? All right. Another one that we talked about that I can really illustrate with this information is that correlation does not mean causation. Okay? Over here, a great example of this, right down here. Nope, I want graph D right here. As your literacy rate goes up, I mean the more literate you are, notice the babies went down. You've seen that graph before. This isn't a new graph. So that means the more you read, the fewer babies you will have. Is that true? No. Just because you're very illiterate doesn't mean you can't have lots of babies. Okay? So right here, there is a good relationship here. It's fairly strong. It's not very strong, but it's fairly strong relationship between these two variables. But just because literacy says as your literacy rate goes up, your total number of births per woman go down, that doesn't mean literacy rate causes births to go down. That's what we're saying. Just because we have a relationship here that's pretty strong doesn't mean that literacy is going to cause lower births for women. So correlation does not mean causation. Just because you read a lot doesn't mean you're going to have a lower birth, fewer babies. Okay? All right. So let's take a look at this. And we're basically, the other thing I wanted to talk about, actually, I'm going to illustrate this in a problem. So you're pretty much, that's really what this is all about. Again, we're not going to figure any of this by hand. I'm going to talk about the constant piece when we got a problem over here in just a second. I'll talk about that. Oh, just to kind of give you another great example of this. In our book, they talk about that there is a correlation that's pretty strong between the number of blankets in Canada bought in a certain month and the brush fires in Australia for that same month. They see that there's a correlation there. The more blankets you buy in that month, the more fires there are in Australia. That's the relationship that you see. Or I think it might be the other way around. Either way, it doesn't matter. But do you think people buying blankets in Canada really causes the fires in Australia? No, they don't. So just because there's a correlation doesn't mean one causes the other. Okay, there's another great example of that. I wanted to make sure I touch base on that. And again, also our book illustrates another one. I always like to give you plenty of examples to think about. The number of liquor stores in a neighborhood versus the number of crime rates in the neighborhood. They see that the more liquor stores that you have in a neighborhood, there was more crime rate. Okay. But is that true? Just because I have lots of liquor stores in a neighborhood means that there's high crime? No. Okay. That's kind of like a stereotype. Stereotypes aren't necessarily true. Okay. They're stereotypes. So just because they see a correlation between the number of liquor stores and high crime rates doesn't mean that just because I have lots of liquor stores, I'm guaranteed to have high crime rates. Okay? Correlation does not mean causation. All right. So, yeah, I wanted to make sure that you understood correlation and the causation and know that it does not matter if I switch the two variables, the R is not affected. It's still the same way. Okay? Okay, so let's take a look at some examples that you're going to run into in the homework. So the first scatter plot, okay, I'm going to actually go to the page width of this. So it's A right here. It says the scatter plot shows the college tuition and percentage acceptance at some colleges in Massachusetts. Would it make sense to find the correlation using this data? Why or why not? So this part B says the second scatter plot shows the composite grade on the ACT exam and the English grade on the ACT. Would it make sense to find the correlation using this data? Why or why not? Go ahead, pause the video, think about it, write it down, or think out loud, and then we'll talk about this. Go. Okay, so for this first one, if you're looking at this, my gut tells me that you do not want to find the correlation. Why? Because this trend looks like that. And that's not linear. The shape of this data starts off kind of, level, and then it curves down. This is not linear. So that's why I would say no to the correlation, because it is non-linear. Hopefully you came to that same conclusion. Okay? Let's fix my R over here. That's horrible. All right. Down here, would it make sense for this guy? Absolutely. Look at this. It's a nice, it looks like it's formed a line. It probably has a pretty high correlation coefficient. So I would definitely say, yes, let's find the coefficient for this, for the correlation. And reason being, because this is linear in nature. As we've talked about before, we only want to do things for chapter 4 is all about dealing with linear trends. Okay? We love linear, nothing else. All right. So right here, first off it asks, would it make sense to find the correlation for this data? Okay. And then they want to know, would the correlation be positive, negative, or near zero? And give it a shot. Okay. So when you look at this, I would definitely say, yes, let's find the correlation, because this is very linear in nature. Okay. So yes, again, because this thing is linear. Anything that's linear, let's find the correlation to. Okay? The correlation coefficient. And because if we look at this, going on to part B, this is increasing from left to right. So that means we want our correlation, our R value, it would be positive. Okay? Easy peasy. And I definitely don't think it would be near zero, because these are pretty close forming that line. It doesn't look like there's no trend. If you are near zero, this thing should look like a mess and you shouldn't see any lines. There should be no trend. All right. So right here, kind of matching. And this is why I kind of gave you in your notes these sets of graphs that are right here. Okay? Because what they're doing in this picture is they're saying, okay, If your R value is 0.767, which of these is the graph? If your R value is 0.299, which of these is the graph? And if you're negative 0.890, which of these is the graph? Go ahead, pause the video, and tell me if this is A, B, C, A, B, C, A, B, or C. Go. Okay. So hopefully you said that graph A is this guy, because this is closer to 1, so it should look like it's forming a line, and it's positive, okay? So the only ones that look like they're forming a line and that are positive are A and B. And because this is closer to 1, I know my dots should be closer together. There shouldn't be a lot of vertical scatter. And A is the one that looks like that. Because B, my dots are a little bit more scattered, almost as if there's no trend. But there is a little bit of a trend here as it, as we move from left to right, it is going up, which means that B must be the 0.29. Because at the end, right here, if you look at this last graph, this is a negative trend. From left to right, we are decreasing. And when you have negative trends, that means your correlation coefficient must be negative. So this guy is the negative 0.98. Okay, and also, this is really, really close to -1, so it should look almost like a negative line. Okay, really, really close, very little variation or spread between that data. See, nothing crazy in this section. And then now, stat crunch time. So it wants you to find the correlation between these numbers. Okay, so I'm going to show you how to use our calculator, and I'm going to show you how to use StatCrunch to get this information. And then we're going to talk about these last two right here, which deal with what I was talking about a moment ago. Okay, we're adding a constant or multiplying a constant does not affect the R. Okay, so let's jump back to this. We're going to do with the calculator first. So in the calculator, kind of going back to this real quick, notice you have two columns. The people column, that's going to go in list 1. The trash column, that's going to go in list 2. Okay, so we're going to go into our calculator, we're going to hit stat, and we're going to edit the list. And in list 1, we're going to put the people, which is 23617. So 23617. And then we're going to scroll over here, and this is where we're going to put the trash. So just make sure, 23617. Okay, so 1833.93. 1833.93. And then we have 2383. Okay. 2383. Now, our calculator can produce scatter plots for us. If you want to see the scatter plot, now that you have this in here, go up to second y equals, because you're opening up what is called stat plots. And all you want to do is turn on plot 1. Okay, because notice it says list 1, list 2. That's a scatter plot formation. Okay, so if you wanted to see what we just put into the list, hit second y equals, hit enter, and then you're going to hit enter again to turn it on, because right now this big black box says it's off. So hit enter. Now it's on, and then you're going to come over and you're going to push zoom, and you're going to go down to number 9, zoom stat, and that will make it so that you can see the actual information that is in the list. So after you hit second y equals and turn it on, see now it says on, hit zoom, scroll down to number 9, which is zoom stat, and hit enter, and there it is. There's our data as a scatter plot. I'd rather use StatCrunch than this. But again, The scatter plot is not what we're after, okay? What we're after is the correlation. Now, to get the correlation for this, here's what you have to do. You need to go to second and hit catalog because you have to make sure that this has been turned on. So you hit second and catalog, which is 0. And you're going to scroll down to what is called diagnostic. I'll show you it here in just a second. Getting close. There we go. It's called diagnostic, and you need to turn it on. So again, hit second, 0, and I do this every time I turn on my calculator if I'm doing statistics. Second, 0, scroll down to diagnostic on, hit enter, and it's ready to go. Okay? You got to make sure that your diagnostics are turned on. Now, here's how you find the correlation coefficient. Go back into stat, go over to calculate. Okay? And this is actually going to be what we also do in 4.3. Okay? So you're learning a little bit of what we can do with the calculator for 4.3 at the same time. And I will review this in 4.3. But you're going to scroll down to 8. Okay? Yes, 4 is the same thing, but as a statistician, and since we are in a statistics class, this is the way that we do linear regression in a statistics class. It's A plus BX. This would be if you were in an algebra class. Number 4 is for algebra. Number 8 is for statistics. So scroll down to number 8, and you're going to hit enter, and then you're just going to hit enter all the way down. Just like what you did for the one variable statistics. Just hit enter all the way down. And what you see right here, this is the equation that models the line. And then down here, you can see your R value. And there it is. Now you know the R value. Okay? The A and B and the R squared stuff, that's going to come involved later for us. But if we didn't turn the diagnostic on, we wouldn't get this information that's down here, the R squared or the R. Turning on the diagnostic is what gives us the R squared and the correlation coefficient. Okay? If we're in StatCrunch, let's talk about it real quick. So I got to turn on StatCrunch. I forgot to do that. Silly Mr. Armstrong. So let's get over to that. Turn on good old StatCrunch. Sorry that I didn't have this ready. I know this eats up a little bit of your time. There we go. Open StatCrunch. Now we got it. Okay. So right here, I'm going to call this people. Right over here, I'm going to call this trash. So our people, let's put that information in. It was under here. So 23617. So 23617. And then over here, we're going to put in the trash, which was 1833.93. Oops, wrong thing. 1833.93. And then we had 2383. 2383. Okay? So what we want to happen now is we want to run a linear regression on this. And if I remember correctly, I thought it was under graph. Just kidding. There it is. So under stat, go down to regression, and you are doing simple linear. Okay? So under stat, go down to regression and simple linear. So select your X variable, that's people. Select your Y variable, that's trash. Okay? And then all we're going to do is hit compute. Now you have lots of information on the screen. In 4.3, we're going to talk about it, but the only thing that you need to concern yourself with, okay? The only thing that you need to concern yourself with, why are you not moving? Come here, you. Okay, there we go. Is right here. See? Correlation coefficient. And right below that, hey, there's that R squared that you saw. Okay? So that's right here. This is the only information that you really need in 4.2. If I scroll to the other page, because it says 1 of 2, I believe the other page shows the graph. Yeah, there's our graph, and there's the line actually put on it. Okay? Pretty cool. So you got both of those pieces of information right there for you. So let's see what it says to round 2. So we have found the correlation between these two numbers. It doesn't say any rounding. I have a feeling it's probably going to make you round to the nearest thousandth, which is 3 decimal places. Okay. So the decimal place for this would be 0.94. Well, actually, the 8 says, hey, 9, go up. So we would say 0.950 according to rounding. Okay? So A is 0.950 because what we had was 0.9498 and the 8 says, hey, 9, go up. So that would become 10. So there's the 0. The 1 carries over. The 4 plus 1 becomes the 5. Okay? So there's the answer to A, which is the same answer we got on both of them. Okay? But I like the StatCrunch better because for this, I have to go up here to my graph to see it, or then now, if I get out of that screen, see, notice all my information about the linear regression is now gone. Okay? So in StatCrunch, I don't lose that. I've got all the information I have right here, and then some, and then I've got my line in my scatter plot right over here. I got both in one place, and I don't lose any of the data switching back and forth between it. Okay? All right, so now let's talk about part B. Part B says, suppose some weight was from the container. Okay, so each container weighs 3 pounds. So we're talking about the trash. So if we subtract 3 from each of these, find the new correlation with the number of people. So we're going to go in and we're going to run this again. Okay, and we're going to subtract 3 from these. But if you remember what I told you a couple minutes ago, if we add or subtract a number, the same number to all of these, does that change the coefficient? No, it doesn't. So what you're going to find out what happens is this thing is still going to be the 0.950. Okay? It's still going to be the same. Let's go take a look. And I'm going to do this in StatCrunch because it's going to be easier to adjust in StatCrunch. Okay? But you do the same thing in your calculator. So we're going to subtract 3 from all these. So 18 becomes 15. 33 becomes 30. 93 becomes 90. 23 is 20. 83 is 80. And we're going to rerun this. Okay? So I'm going to hang on to this. And we're going to do stat. We're going to run regression, simple linear. And again, we're going to do the same thing, except this has the new trash. Check this out. Here is my original. Here is the new, because we subtracted 3. It's the exact same. That's what I mean in that beginning when I said you can add a constant. So I can go to all the people and say my house is increased in size, and I can add the same constant to all these. It has to be the same every time, just so you know. It can't be different numbers. But I can add the same constant over and over and over again to all of these, and my regression will, or my coefficient stays the exact same. Okay? Or I could subtract the same constant from all these over and over and over again, and it will still stay the same. Because all that happened between these two graphs, I'll show you. All that happened is my points got shifted down by 3. That's all that happened. See how the 20, it went down, or the 23 went down to 20. This was the 18, it went down to 15, although it's a little harder to see at these, but all that happened is I just moved all my points down. There's still the same vertical distance away from each other. Okay? So that's why it doesn't change. And the same thing happens if I multiply everybody by a constant, which is what part C is about. So part C says, what if there are twice the number of people in the houses, but the weight stayed the same? So we're going to keep that same weight that we did over here. We added and subtracted the constant, right? So what happens to the correlation if we multiply by a constant and nothing happens to it? This answer is going to end up being 0.950. Okay? It's going to be the same answer as before, because adding constants or multiplying by a constant does not change it. So if I go in here, this is the original information. So let's go over here, and there are twice as many people. So that's 4, 6, 12, 2, 14. Let's run stats on this. Stat regression, simple linear, X is people, Y is trash. Compute. Same information again. It did not change the correlation or the R squared that you saw before. It's the exact same. And notice I did 2 things on this one. I mean, I could have went back to the original trash and had 18, 33, 93, 23, 83, and it's still going to be the same thing. But here I multiplied this by a constant and I subtracted by a constant over here. It's still the same correlation. And again, if you look at the graphs, okay, it pretty much looks the same thing. Okay? So I believe this was the new graph. Okay? This is the old graph. So this was the original data. How do I know that? Because up here I've got 23, and then right here, if I hover over the point, you can see that it's 2 and 20. All that happened is that it's like it shifted my graph to the left. Okay? So instead of starting at 1, I jumped up to 2. Okay, and this guy that was 2 jumped up to 4. It's like I moved my graph to the left. Okay? It did not change the correlation coefficient. And just one other piece, because we've got the data. Remember I said that it didn't matter if we had people first, then trash? I want to show you what happens if we reverse it, because I can do that really quick in StatCrunch. So let's go to regression, simple linear. Let's say that this is trash and this is the people. Look, it's still the same. Now, when you look at the graphs will actually be a little bit different. Notice my line's a little higher now, but it's still the same information. Okay? This still has the same correlation coefficient. It's kind of like the dots got reflected over a line a little bit. Okay? It's still the same correlation coefficient. It's still that 0.95 here. It's still 0.95 here. So it doesn't matter if you switch the x and the y variables around. The correlation coefficient will stay the same. Okay? Kind of cool. So that right there is the end of 4.2. 4.2 questions fall from question 11 to question 23. So that's it for me. Catch you on the flip side.